In this video, we're going to talk about a special type of statements called quantified statements, and in particular the quantifiers that make them quantified statements. We're first going to define what quantified statements are. We're going to define the universal set of a quantified statement. And then we're going to focus on the two types of quantified statements that are most important in mathematics. They're called the existential quantified statement and universal quantified statements. And those are the statements that have there exists and for all in them. We're going to figure out which quantified statements are true, which one are false, and how to determine that. And then finally we're going to figure out how to find negations of quantified statements. A lot to do, so let's get going. So a quantified statement in general is a statement that answers the question how many. So if you ask how many, it answers that question. So for instance, how many real number solutions does the equation 2x plus 3 equals 9 have? Well, you might answer that correctly, actually, or incorrectly. If you answer it incorrectly, that's also a quantified statement. That actually happens to be a false one, but this is going to be a true one. Our quantified statement is going to be there is exactly one real number solution to the equation 2x plus 3 equals 9. Notice that is indeed a statement, and it answers the question, how many real number solutions does it have? Here's another question. How many people are asleep right now? And, you know, your guess is as good as mine, but I'm going to be safe and say there are at least 100 people who are asleep right now. Notice that I didn't answer exactly how many people are asleep, but I did give a statement about the number of people who are asleep. That's a perfectly nice statement and almost certainly true. I'm sure there are at least 100 people. In fact, you're probably falling asleep right now too. Wake up! All right, so our next question is how many of the natural numbers are prime? Well, I'm going to answer that. There are infinitely many natural numbers that are prime. And, you know, that's not the only way you can answer that quantified statement or that question correctly, but it is a true quantified statement. So, if we're trying to construct a quantified statement, one of the things that is important is the universal set. Anytime we've been dealing with open sentences in previous videos, we're always asking what our universal set is. And the universal set, so our quantified statement asks how many and answers that question. The universal set answers how many of what. What are we actually looking for that we're counting how many of them? So when I say there is exactly one real number solution to the equation 2x plus 3 equals 9, that answers the question how many of what? We're asking how many real numbers. We're talking about real numbers. That's our universal set, the set of real numbers. If we're talking there are at least 100 people who are asleep right now, what are we talking about? We are talking about people. Our universal set is the set of all people. If we're talking about there are infinitely many natural numbers that are prime, here we're talking about natural numbers, the set of natural numbers. That's our universal set. In general, the universal set of a quantified statement is the set of objects that are being considered for that statement. So there, as you can see, there are as many quantified statements as there is imagination for answering quantified questions. But we're going to concentrate on what are probably the most important quantified statements that are in mathematics. You know, someone can prove me wrong on that one, but I'm gonna go out on a limb and say these are the most important. They are the existential quantified statements and universal quantified statements. So we're gonna let D be the universal set, and we're gonna let P of X be an open statement where the variable X represents an element of D. So D is the universal set. Those are the things that we're thinking about. P of X is an open statement. X is in our universal set. Standard setup for open sentences, right? So let's see. Our existential quantified statement is going to sound like this. There exists some X in D such that P of X is true. Right? So anytime you have a statement of that form, that is an existential, or if you say a there exists statement, that'll be fine too. I won't give you trouble, I promise. So when is this going to be true? When is it going to be false? Well, there exists means it's going to be true if P of X is true for at least one value of X in D. In principle, you have to look at all the values of X in D, but for this one, if you happen to find one X in D that makes it true, you can stop your search, you know it's going to be true. And that also means on the flip side it's going to be false. The only way it's going to be false is if P of X is false for every single value of X and D. Because again, if even one of those values of X and D makes it true, the existential statement is true. All right, next is the universal statement. Universal statement looks like this. For all x in D, for all x in our universal set, P of x is true. Now, when is that one going to be true? Well, the for all means that it's true when P of x is true for every single value of x in D. So we look at all the values of x in D. If they all make P of x true, that makes our universal statement true. And that means false is when P of x is false for at least one. Because again, even if it's false for one, it can't be true for everyone, and so it's going to make it false. All right, so here's some examples. Here's an existential one that we might want to look at. Oh yeah, this is an existential that we've looked at before. There exists x and z such that 3x plus 4 equals 5. And I'm not worried about whether this is true or not, but it's a fine existential statement, right? So the universal set, well, let's see. What are we talking about? We're talking about x in the set of integers. So the set of integers is our universal set. Our p of x is 3x plus 4 equals 5. Right, 3x plus 4 is our subject, equals is our verb, and 5 is our object, and x is our variable. And let's see, if we want to find out whether or not this is true, let's see if we can find any integers that makes it true. We're going to go ahead and solve for x. That's one way of doing this. We find that x equals 1/3. That is not an integer. That means every integer of x makes p of x false, which means that our existential statement is false. Ah, well, that's the way it goes. Now, for a universal one, if we look at for all x in the real numbers, x squared is greater than or equal to 0. Again, let's look at what our universal set is. In this case, we're talking about real numbers. So x is a real number, so the set of real numbers are, that's our universal set. Our p of x is x squared is greater than or equal to 0. And if we want to know whether this thing is true or not, well, we got to look at it's a for all statement, so we got to look at every single possible real number. What happens when we square it? Well, if we square a real number, we always get a non-negative. We can't get a negative number by squaring a real number, which means that if x is a real number, x squared greater than or equal to 0 is always going to be true. That means p of x is going to be true for every real number x, and that means our statement is true. So before I let you go and work on some of the activities, I want to talk a little bit about negations of quantified statements, because those are a little bit tricky. So, and again, if you want to think about what negation of a statement is, generally it is a precise way of saying what it means for the original statement to be false. So let's look at our existential statement. There exists x in the integers such that 3x plus 4 equals 5. Let's see if we can figure out a useful negation for this one. And in order to do that, I want to know when it's true and I know when it's false. So let's start with it's true, because that's a little bit easier, and then I'll figure out when it's going to be false, and that's going to help me figure out my negation. Now, it is going to be true precisely when 3x plus 4 equals 5 is true for at least one integer x. It could be more, but at least one. Okay? That means, flipping that over, the only way it can be false is if that equation is false for every single integer x. Because again, if even one of them makes it true, the existential statement is true. So it's going to be false if 3x plus 4 equals 5 is false for every integer x. And you might notice a funny little phrase in there, that for every. And if you're thinking about what we've just been talking about, that's a for all statement. So saying what it means for that statement to be false is a for all statement. So if I want the negation, that is itself going to be a for all statement. And if I want to sort of reorganize things so that it looks more for all like, it's going to be for all x and z, 3x plus 4 equals 5 is false, or 3x plus 4 is not equal to 5. So we took our existential statement, when we negate it, it becomes a for all statement. Let's see what happens when we negate a universal statement. Something similar is going to happen. You may not be surprised by that. So let's say we have for all x in the real numbers, x squared is greater than or equal to 0. And again, this is going to be true precisely when x squared is greater than or equal to 0 is true for every real number x. And if we flip that around, that means it's going to be false if x squared greater than or equal to 0 is false for at least one real number x. Remember, if it's false for every real, for no real numbers x, that means they're always true. Your universal is going to be true. So it's false if at least one real number x makes that inequality false. But at least one, gosh, that looks very familiar. That is a there exists statement, right? At least one means there exists. So we take our universal statement, we negate it, we're going to get a there exists statement. If we rearrange what it means for the universal statement to be false, that means there exists x in R, that's for at least one real number x, such that now x squared greater than or equal to 0 is going to be false. That means x squared has to be less than 0. All right, so now that you've had a chance to think about how quantified statements, how to figure out whether they're true and false, how to negate them, I think you're ready to work on the activities for quantified statements, and that's on the file included with this video.